Okay, so we finish this last thing that I was talking about last time. So I was sort of in the middle of giving, if you wish, the kind of dissenting opinion with respect to the general manufactured consent about the functioning and properties of large language models and their handling of the properties of language, and in particular syntax. So there were actually just two main observations that I was doing. Well, let's say three main observations that I was doing last time. So one is the fact that, you know, this particular technology and technology in general is never theory neutral. So there is always some kind of theory, whether people explicitly acknowledge it or not. There is always some kind of theory behind, you know, the structure of a particular technology. And this is true for the case of the way that large language models are designed. The underlying theory of language is a very specific theory of language, which is Zellik-Harris distributional theory, which is just about 80 years old, and also just about 70 years obsolete from the point of view of the theory of language. And so this is, you know, the underlying idea about how to model syntax is based on, you know, the old behaviorism and the idea that one, you know, only looks at probability distributions of text, strings of text included inside other strings of text. And the second observation that I was making is that, you know, despite the fact that, you know, this is the underlying, you know, theory on the basis of which the technology is designed, you know, whether explicitly or implicitly, there is something that is happening, namely, you know, the computational mechanism of syntax is in some sense, in some way, recovered from data that have to do with proximity inside the vector model of semantic space. So what is effectively happening is that there is an inverse problem of, you know, how to reconstruct a certain computational mechanism that is being solved to some extent. Right? And of course, in general, you know, this is a general well-known fact in mathematics, that solving inverse problems is extremely hard. And so one can expect that you will get some kind of, you know, partial solutions or you know, where the question will be to what extent this can be done. And the other thing, so this is like the second point, that there is this question, you know, how the computational mechanism of syntax is or can be, or to what extent can be reconstructed from this data of semantic proximities in a vector space model of semantic space. And the third observation is that there's a certain number of empirical tests that I've been discussing last time that have to do either with actual estimates of dimensionality of the text produced, or with specific investigation of the handling of specific phenomena in syntax that seem to indicate that there are boundaries to how well this problem of reconstructing the computational mechanism of syntax can be achieved, at least in the present versions that are being tested, and with the specific kind of tests that are being done. I mean, but there seems to be limitations, and you know, one can see that, you know, indeed there's an imperfect handling of more sophisticated, you know, syntactic structures. And this, you know, one can think that, okay, maybe it has directly to do with the fact that the underlying theory that models language is a theory that has its own, you know, limitations. And these are reflected in the way that this you know, computational mechanism of syntax is recovered. Or it could be that there's an intrinsic limitations to how you can recover the computational mechanism of syntax. So this is, in a sense, is a question of what one can understand about this. And so, in a sense, that's what I'm saying. Okay, you know, one can take a kind of you know, very pessimistic view on this, but one can also, you know, more pragmatically and in a sense more interestingly, take a more optimistic view and try to understand what one can derive, you know, what kind of information one can derive from these experimental apparatus, which are the large language models, about this issue of how to reconstruct the computational structure of syntax from semantic proximity data. Okay, so let's look at it in that sense. Okay, so this one can say that from a theoretical perspective, one can consider this as an interesting question to investigate. To what extent the computational mechanics that govern the syntax of human languages can be reconstructed. Okay, so this in a sense means that you wanna, so one of the ways in which one can think about approaching a question like this is to try to open up this black box that these type of machine or neural network structures are usually considered to be. So this is something that actually many people have been considering, not just for the purpose of the question that I'm talking about, but just more generally. And it goes under the name of mechanistic interpretability. And it's a way of saying how much one can try to reverse engineer the computations that are carried out by certain kind of neural network architectures and try to understand what are the actual circuits that perform certain kind of calculations. And so so people talk about identifying certain simple algorithmic patterns that we call motifs inside the architectures of neural networks. So again, this is again something that's from the theoretical point of view goes back to the same framework of Zelliker's distributional theory. In fact, he was proposing this idea of mechanical procedures that would be designed to discover basic elements of language and transformation from these probability distributions of the inclusion of text inside other texts. And to some extent, you want to, so when people talk about the mechanistic interpretability of transformers, they actually are revisiting exactly this idea in the sense that you have, the probability distributions are the ones that are computed by the attention modules in the way that I was sketching last time, and I'll discuss more in detail this time. And the idea is to try to extract some kind of mechanism from that and do actual computational circuits from those. And of course, if one attempts this point of view, this usually works on very small models because you try to actually identify very specific elements that are understandable in smaller version. For example, one can look at what happens when you have 1 or 2 layers of notation module. By comparison, the typical things like GPT, I have 96 layers or something. So the order of magnitude is obviously different. But some things do emerge that have some interest, and I'll say in what sense I think that they are actually related to the question that I'm interested in discussing. For example, this notion of induction heads that provide a certain kind of in-context learning algorithms that one can see. Okay, so I'm going to follow one particular reference that talks about a model for this kind of transformer circuits and how to investigate these structures and transformers. So first of all, the kind of models that one looks at in this context are very specific ones. They're ones that are autoregressive decoder only, like GPT, not the kind of encoder-decoder structure that is used for task-like translation that have an additional layer of complication. And they are attention only. So in the sense that I'll show this in a moment, normally the way the transformer architecture works is it has attention layer and it has some multi-layer perceptron layers. And those are more complicated to reverse engineer because there's like these deep neural networks are in general more difficult to reverse engineer. But it seems like especially from the point of view that we are interested in of trying to detect where syntactic structures are stored and the calculus of syntactic structures is stored, is the attention modules that are the most important part. So one can sort of momentarily forget about these multi-layer perceptron parts. Okay, so so basically the transformer operations are these basic ones. There's a token embedding that realizes parts of words, let's say words or parts of words, tokenizations of words in terms of vectors inside some semantic vector space model of semantics. And then there's a series of transformations, which are referred to sometimes as residual blocks. And these have this kind of different type of blocks, attention layers, and these with multiple attention heads in parallel. And now I will get back. I was previously ignoring this fact, but now I'll get back to say more about that. And these other MLP layers. And then at the end, there's a token unembedding that produces the final outcome of the next word, next token. So the structure is something like this. You have an input, which is your input prompt. Then you will know this gets embedded in as vectors in your vector space. And there is this residual stream part that I'll talk about in a moment more, which is where these vectors they are stored and are transformed. And there's a certain number of layers. There are these multiple attention layers. Each one of them takes an input from the residual streams and transforms it in a way that I'll say more, which I kind of sketched before, and I'll say more about now, and then adds it back into the main residual stream. And then there are these multi-layer perceptron parts that continue, and then you can have several modules like this, and at the end, you have this unembedding that produces the final output. Okay, so this is the basic structure. So the first very interesting and important observation is that the residual stream, which is also known as the embedding, so this is this vector space model that you have for semantics, and this is all run, the residual stream is all run by linear operations. So it is really linear operations on a vector space that take place. And the linear structure of the residual stream is actually used for one important thing, which is, I've been using this several times before, the fact that when you have to keep track of a list of different, say, possibilities, or at the same time, you just write them as a sum inside some vector space. And so this is the same idea here. So it allows you to store in different, so this is a very, very large dimensional vector spaces that, at least 200 of dimensions for a small model, 10 to the 4th for a large one. So you have a lot of different subspaces. So you have room for storing, in linearly independent pieces of information into a lot of different dimensions. And so that's exactly the way in which it's used. It's a way of having a dimension in which to keep storing information that's independent, that can be kept independently of it, each piece independently of the other. Okay. And so different information gets stored in different subspaces and gets sent to different layers and taken out and in by different layers. And each attention head actually operates on a very small subspace, typically of about 64 dimensions. So this doesn't mean that the actual matrices that represent your linear operator are huge. The typical way, even in this very small model that I looked at, is like 50,000 times 50,000 matrix, but of rank 64. So they are extremely sparse things. And the subspaces, this will take out certain parts, take from certain parts of the residual stream and put it back in other parts of the residual stream. And so it's like the subspaces are like different memory storages that they were a lot of additional, with a lot of additional subspace you keep storing from different levels, different layers. Okay, so I just sort of draw the picture of what happens. At each layer you have some linear operator that reads out of the residual stream. Then something is computed that I'll get to in a moment, and then each layer writes back into the residual stream the additional linear map. And so you can, to some extent, you have the possibility of either combining or storing in separate parts the results of different layers along the structure of the transform. And so different layers can interact if they're writing and reading on the same piece on the same subspace of the residual stream. And you can, for example, take out something and cancel it by reading a vector and adding it the inverse one so you can remove parts or you can add parts into the whatever piece of the residual stream you want to act on. And now what is happening with the attention heads? So the primary functions of the attention module is to move information around between different parts of your residual stream. And and you have like multiple independent attention head at every layer that compute with a massive parallel computing. But you can really think of them as adding them together as a single operation that happens, a single linear operation that happens on your residual stream and then puts back your resulting vector in the residual stream. And so the point here is that you can think of the various coordinates that you have in your vector space as being roughly separated into two parts. There's a part of the coordinate that has to do with this embedding of the words or the tokens into your semantic space, and there are positional coordinates that actually take into account the fact that you want to work with strings of text as ordered string of text. So you have coordinates that will keep track of the various positions and the relative positions. So the attention part of the module is gonna primarily affect the positional variables. And there's another independent circuits that is going to affect the representational coordinates on the residual stream. Okay, so what is the part that pertains to the attention head? Okay, so you have your is the input that is coming from that is in the residual stream at that step, the ith step. And so you have one linear transformation that acts on it and produce this vector, value vector, which is again deposited in the residual stream. And you can compute so you have a certain attention matrix, which is the one that is computed by certain, that is based on computing certain probabilities that I'll remind in a moment how. And you weight these value vectors with the probabilities that are computed by this matrix. And this gives you these result vectors at the level R. And so your output vector that gets put back into the residual stream is again a linear operation applied to this result here. So the combined operation is something like this. And the tensor product here is separating out the parts of the vector space that takes into account the representation of tokens in the semantic space, and the part that takes into account the positional relations. So you have a part that is acting on the positional and the part that is acting on the representational part. And these two are independent circuits. Okay, so this part mixes between the tokens, and this part acts on each of the token representations independently. Okay. So now, as I said, for the way the part that acts on the positional coordinates of the tokens, which is the attention matrix, is obtained as a probability distribution, which is constructed from these other two linear operations, which are the query and key vectors that are computed from the input on the residual stream. And then they are combined in the sense that you evaluate in the process, you evaluate the proximity in semantic space, and you use that to form this probability distribution with which you weight these value vectors. So these are the three matrices that play the role in the story. the one that computes the key vectors, and the one that compute the values, and these two are used together to form the media attention matrix. So there is only one nonlinear thing that ever happens, and the only one nonlinear thing that ever happens is this forming of this probability distribution by this softmax operation. Everything else is linear, and this once it's formed, it's itself acting as a linear operator on the vectors. Okay, so the only nonlinearity is constructing this probability distribution. And so the result of each attention head is this probability distribution applied to the value vector, and the outcome, the final outcome, is these operations on the embedding dimensions of in the space, and this attention transformation on the positional part. So this means that there are these two separate circuits, this vector per token side and this position side. Both of them are given by extremely sparse matrices. One of them is reading the source token and writing to the destination token. And the other one is moving information between different tokens. And the only part that implies this nonlinearity, nonlinear construction of probabilities. And the other thing is that one thinks of this as depending on these matrices, but in fact it depends on less than this, because this only ever occurs in this product combination. So in fact, any other decomposition, so it's kind of convenient to think of them in terms of this kind of decomposition, but any other decomposition that would keep the same products would give the exact same results. So it's a bit of a redundant explanation to think of them in these terms. This is really what matters. Okay, and then there is this other fact that if you have when you have multiple attention heads, they effectively function as a single combined one, in the sense that these two channels separately compose. And this composition, you can, although there are these nonlinear effects, which are here is where the nonlinearity is actually important, but you can effectively think of this as being a single channel on attention. Okay, so I'll come back to unravel what is happening more precisely in a second. Okay, so now let's sort of break this up into the minimal possible constituents. So first of all, let's think of the case where you have a zero-layer transformer. So nothing happens except embedding and unembedding your token. Okay, so what is this doing? So of course, these are all things that you optimize over, right? So you want to try to compute what is the optimal, the maximally probable output. Okay. So if you are in the zero-layer transformer, then all you have is this composition of two linear operations, the embedding and the unembedding. And so what is the optimal possible behavior? It's a diagram model. Right? The maximal possible behavior that you can get is to optimize the probability that of the next token given the previous one. That's all it's doing. And so it's this thing is actually computing the log likelihood for the diagram model. Okay. All right. So this is saying that so you have one part that's going straight through the residual stream, and is mapped exactly by this thing. So it means that you always have this background diagram that is always there. And then whatever you have you have another channel that is going through all the other layers, but on the background, you always have a diagram model. Okay. And the thing, so when you break up what this is doing in actual thing, this is actually only visualizing very elementary kind of a binary combination. So an example that they identify, for example, if you're looking at the corpus of English literature taken from the web or whatever, if you encounter the word Barack, it's very likely to be followed by Obama. So this has nothing to do with syntax, has nothing to do with the theory of language. It's just an elementary diagram, okay? So this residual stream that goes straight through is an elementary diagram of that sort and identifies this kind of completely stupid correlations. Okay, so that's all it does. Okay, so this is fine and it's not particularly interesting. So now what is interesting is what goes on in these other parts.
Does that happen in this zero layer? Are there other streams?
Yeah, so if you have the zero layers, that's all you're gonna see. So if you have nothing else, you don't have any attentional nodule, you just have this embedding and unembedding. You know, what is getting optimized is exactly capturing these elementary diagram relations. Okay.
But elementary diagram relations can still say something about like grammar, right?
Yeah, but the thing is that there could be things that have nothing to do with grammar. In fact, most of the time there are things like this thing, like names of people, things that go together not because there is a linguistic relation in them, just they go together because of reason like this. And so this typically sees those kind of things. Okay. All right. So now we have something more. So one layer transformer, where you have this background diagram, and you have one thing that is only an attention module, no multi-layer perceptron, just a single multi-head attention module. Okay. So again, you have the same things as before, the token embedding and the unembedding, and so whatever goes straight through is this diagram. Now, what's interesting is what goes through this. Okay, so here's what is going on. No, the embedding and the unembedding we have already seen, and now there is this attention layer. So this part is just saying that you still have the one that we discussed before. So you will still see those elementary diagram relations, but you will also see something new. And this part is the one new. This is this weighting of these value vectors in terms of this constructed probability distribution. Okay, so this part itself has two separate parts, okay, two independent circuits. One that is only acting on the embedding measure, and one that is acting on the positional variables. And so so one can, because this is just tensor product, separation of the two parts of the space, one can just separately look at what these two circuits are doing. Okay, so these are the two circuits in parallel. Okay, we should think of it this way. So these are the source and destination tokens in your list of positional relations between them. So if you are here at the destination token, you are looking at what is the previous one that is most attended to. In each of these attention head that you're computing, you look at what is the previous one that is most attended to. And this is what this circuit here, the key and query circuit is doing, is searching for that, or identifying one that has this that maximizes this probability. And then the other parallel circuits is saying what effect this has on the output that you're going to write now on them as your next step. Okay. So these are the two separate circuits identifying a particular token that preferably attends to, and given that the token that is attended to, how that will affect the output. So what is this one-layer transformer? So this one-layer transformer is also something that is well known. It's called, and so there's something that is called a k-skip n-gram. So the n-grams I have already discussed long ago. This probabilistic models of Shannon, so that look at probabilities of n strings, making them this kind of hidden model type description. But a k-skip n-gram is the same as an n-gram, but it looks at possibly non-contiguous substrings where the skips are of a given length k, or of arbitrary lengths if you don't specify the k. So what this one-layer transformer is, it is a skip trigram. where the trigrams are, the source, destination, and output. So this functions exactly as a skip trigram. And again, the matrices themselves are enormous, but their actual rank is limited, and one can explicitly read. So what you do here is a kind of direct search. So you have these 50,000 and 50,000 matrix. Its rank is actually only 64. So one looks for the entry, by brute force, you look for the entries that are largest, and you see what those are doing. And so that's how you identify that this is actually a skip trigram. Okay. And so what is the conclusion that one draws from this one layer architecture? So most of the attention had now one is just by looking at what is actually doing something in this. So the things that are actually doing something, most of these attention has in this one layer are copying. So they are copying pieces from one position to another position. As I said, you can get to store a lot of things in many of these dimensions that you have in your vector space. So you can, in the vector that corresponds to the representation of one token, you can store copies from other positions. So part of what is happening is exactly transferring information from one of the positional coordinates to another one. And this what it will do effectively is to identify simple trigram relations. Like, for example, if you have combinations of three words that occur like back and forth, eat and drink, day and night, keep in mind, keep at bay, it will identify those. We will see the matrix entries that gets activated are corresponding to these kind of things. And but the thing is that here is something interesting in the fact that you have these two parts of the channel that are completely separated as two, as factored with respect to this tensor product, is that it will not quite work completely as a trigram, because it is not, you don't have like the complete triple relations, you just have pairs. And so what it will also, so the effect what you will see explicitly is that, for example, if it's giving high probability to things like keep in mind and keep at bay, it will also give high probability to things that don't work, like keep at mind or keep in bay, because of this factor structure. Okay, so it's so this is the kind of things that you see, and also the thing that you can observe if you look at where are the the non-trivial parts of this enormous matrices is that in the case of most of your parallel heads, the things that's most attended to is just the previous token. And you find this is the one layer thing. So in this one layer thing, where you have many heads in parallel, but organized serially. So they only have one layer of attention module. And then you will typically correlate only with the nearest word. So this, of course, would be very bad news if we are actually looking for syntactic structures and syntactic phenomena, because we know that syntactic relations depend on long distance relations that are structural relations in a tree, but they don't happen to correlate to the local proximity in the string of text. And so something else has to happen for any mechanism that is actually associated to computational syntax to take place. And this is where you actually do need more than one layer of attention, not in parallel, but organized in a serial order. So what happens if you now have two layers of attention modules that come one after the other with respect to the residual string? So you now have two packages like this. And so the fact that each time you have this part that goes straight through the residual stream means that you will still get what you had with a single layer. So those actual simple trigram relations, you will still see them because you still see what you had in the single layer. You will also see the very basic diagram relations, because you also have the thing that passes through the residual stream directly without getting anything in and out of the attention modules. But now you also have the part where the attention modules are composed with one another. And this is actually the only thing that allows you to try to have something that will reflect the actual structure of syntax. So there's no way to do that without having multiple layers. All right. So now you have this new circuit. You have this new circuit that has this composition here. And that's the part that is becoming interesting. So the observation that I made before is that you can think of this composition of two attention transformations as a single attention transformation for the kind of composed set. Of course, what you have on this side is kind of the formal definition, which is that composition, because these are nonlinear operations. And correspondingly, you have this output and input into the residual stream that also separately composed, because they are on the two sides of the tensor product. Okay, so at this level, again, you can look at what are the actual entries that are non-trivial in this matrices, and what one sees at this level is that now you can have attention heads that attend to tokens that go back to other positions where it's maximized for tokens that go back to other positions that are not immediately adjacent ones. And so, for example, you can get things that optimize where the subject is located, or that go back to look at the beginning of the sentence, or things like this. So it's not just adjacency relation. Of course, there are some basic syntactic relation that you can see just by looking at the adjacent word, because they just happen to correlate to the fact of being nearby words. So an adjective that modifies a noun is very often coming next to the noun, and very often subject and verb happen to come in nearby position. But there's as you get to deeper and more interesting syntactic relation, that completely decouples the position, the linear position in order to the actual structural position in the tree. And the thing is that this composition of attention heads is where you can actually see longer distance correlation that actually correspond to relations that happen in a syntactic tree rather than in a string of text. And so there's also this phenomenon. You see that they are this thing that they call induction head. So these things are often called virtual attention head, because this is really not a single attention head, but you just model it as if it were a single attention head. And there's this other notion of induction head, which are also visible from looking at where the weights are concentrated, which are things that keep attending to previous copies of the same token that reoccur. And this is like thing that correlates to syntactic relation like co-indexing, where you know that a certain part of sentence is referring back, or anaphora, these kind of things that when perhaps it refers back to its previous occurrence. Okay, so now the thing is, so this poses some questions for which at the present state I don't have an answer. Maybe hopefully at some point we get back to something more about this, but one can ask certain specific questions. So the point here that this idea of trying to recognize circuits inside this kind of architectures of transformers. Transformers are quite suitable for this precisely because most of what is going on is linear. So unlike the deep neural network, recursive neural networks, you actually, it's easier to try to identify actual circuits that do operations in transformers. But I mean, this idea of this mechanistic interpretability in its most general formulation is again, in my opinion, too biased by this behaviorist idea that you just look at the distribution, you try to guess what is the point is that we know what we should be looking for. That's the main difference with respect to the behaviorism attitude. The fact is that if you actually have a theory of language, you can make a prediction for what you want to find. And then you can use an experimental apparatus to try to verify where your model is manifest in the data. And so the question that one can ask at this point is that, okay, we know a certain mechanism that know how syntactic structures look like and how they are generated. And so if something is composing languages, where are these operations taking place? Well, we know what the operations are. So the point is, where are those operations taking place? Right? So that's a much more specific question than just, what are these probabilities in a more vague sense. And also one can make these questions more precise, like, for example, how does the depth of syntactic trees correlate to the layers that you need in order for the computation that generates it to actually take place? And I mean, it's quite natural to expect that there is a correlation, that after all, as humans, there's a certain, like in these tests of syntactic structures that I was mentioning last time, the ones that are done on humans, there are some that are more difficult for human users of human language to actually parse correctly. And most of the time, it was because there are some depth, or some actual tree structures that are more complicated that you have to parse. And those very often also happen to be the most difficult for the machines to parse, but also find difficult other things that humans don't find difficult. But the point with this is that there's empirical evidence that seems to at least support this working hypothesis that one can test then data, which is to what extent the depth and the layers correlate. And whether this varies according to specific syntactic phenomena or not, because we've seen that different syntactic phenomena have different kind of responses from the large language models. And specifically, if one wants to identify circuits, then we have specific operations. So what is the circuit that actually performs the merge operation of syntax, for example, which is the basic structure building operation, and also the basic parsing operation. Okay, so this is like what I consider a reasonable program, but there's a couple of cautionary tales that I want to discuss at this point. And actually, the reason why I want to discuss these things is because, to me, one of the most dangerous aspects of the current propaganda around the large language model technology is the issues surrounding the difference between prediction and explanation. And I mean, there's a paper that was written last year at some point by someone who is actually a linguist at Berkeley, whom I'm not going to mention by name, not out of consideration, but because he doesn't deserve any publicity. But so normally one puts out the paper, one worries about things being trivial, or things being known, or things being wrong. And some papers, pretty much everything that they contain is trivially known to be wrong. And, and this is kind of problematic. So anyway, there is such a paper by someone who is a notable linguist at Berkeley, and claims that the large language model disprove the theory of language in generative linguistics. And the argument for that claim, if one can dignify it with that word, is roughly goes like this. So first of all, this technology is theory neutral, which I'm arguing is not. And therefore, it is itself a theory of language. I mean, apart from the complete non sequitur of the therefore, I mean, I just want to make a point of the fact that either someone is completely confused about the meaning of the word theory in science, or it's worse. So what is the point about the difference between prediction and explanation? Well, let's talk about large language models. So it's something that is perfectly technologically doable. And I mean, some people in this room can do it in their sleep, is to actually take a large language model and train it on a particular data set, which is the SIGLA data set, which is the complete collection of all the 772 texts of the language linear A that are known, that have ever been found. You can do this. You can train a large language model on that data set, and it will produce the next word in linear A. Not a single person in the world will be able to tell you if that is good linear A or not, because linear A is the undeciphered language of the Minoan civilization of Crete. There hasn't been a single speaker of linear A since the year 1400 something before current era. So we will have a machine that makes prediction. What has it explained about the language linear A? I would say absolutely nothing. So making predictions is not the same as understanding. There is a specific reason why I'm making this example about the linear A speaking large language model. Because there is another language that is called the linear B. And the linear B is not an undeciphered language. On the contrary, is an extremely well-known language, also known as ancient Greek. And the story of the decipherment of the linear B is actually very interesting in the perspective that I was just been talking about what is the actual underlying theory of the large language model, because this is the one success story of Zali-Harris' distributional theory of language. The main crucial step in the decipherment of the linear B was provided by 3 papers that were published between the year 1945 and the year 1948 by Alice Korber. And these were actually based on the distributional theory, probabilities of text included in other texts. The point of this is that this idea was actually used to probe a scientific hypothesis. So you have a theory, a model, and you use some techniques of effectively data analysis to probe your theory model. What were the scientific hypotheses? So hypothesis number 1, that linear B was an inflected language. So this means that you have your words break up into pieces. There's a root of the word, and there are suffixes that corresponds to declension of nouns and conjugations of verbs. And the statistical analysis of inclusion of types confirmed the fact that this was in fact consistent with a syllabic alphabet, where the syllables would break up into root parts and suffixes that would correspond to noun declension and verb conjugation, with certain bridge syllables that would serve as grammatical connections between these 2 parts. This was paper number 1. Paper number 2 was again the statistical identification of possible phonetic relations between these different elements of the linear B. And the final step, which actually was completed, and Kober died very young, and after this was completed just a few years later by Ventris and Chadwick in 1952, which was again the comparison between these patterns and the ones of a very well-known language, which was ancient Greek, and the fact that these completely matched. And so the conclusion of this is that linear B is ancient Greek, Mycenaean Greek, so kind of an earlier version of what would become Homeric Greek and then archaic ancient Greek. So the point is not, so the point that I want to make is that the fact itself that the functioning of the large language models is designed on this distributional theory of language, if one acknowledges the fact that they are not theory neutral, that they are representing a very specific theory of language, can be used as an experimental apparatus for interesting results, provided that the theory is coming from something else that you are testing using an experimental apparatus. Okay. So second cautionary tale, about this claim that the large language model in themselves constitute a theory of language. So why does something?
Can I ask? So did anybody do the same for linear B than they did for linear A?
Yeah, so that the same thing analysis does not work for linear A. That's
what I mean. Take a large language model and train it on linear B without telling the number we speak or something.
no. So as far as I know,
Send text and see it produces good linear B.
that's a very interesting question. I don't think that anybody has done that. So I don't think that anybody has played with this kind of languages and
If the output were that it is good linear B, then one might imagine that the output of the first
would be good linear A. Yes, no. So
extend the corpus of linear A by factor of 10.
yes. So as far as I know, nobody has done this kind of game with linear. I'd be interested in looking at what the result would actually be. But yeah. So we will have some nice artificial intelligence, going around speaking ancient Greek, which I think would be exceedingly cool. And so, okay. Now, the other cautionary tale about why it doesn't make sense to claim that the large language model themselves are a theory of language. Okay, so this is a story that comes from the lab next door, your lab, and so one can look at these architectures in terms of control theory. So what is the test here? So you have a certain prompt, so a certain initial state that you feed your large language model, and now you want to add to your prompt a certain control sequence in the smallest number of possible tokens that you want to add that will maximize the probability that the next word that is output is a one of your choice. So kangaroo. You have a given prompt, and you want the next word to be kangaroo. What do you add to your prompt? Now, of course, if you think in terms of a theory of language from our biased human perspective, what you would imagine doing is to try to steer the semantics of your prompt towards something that would involve a kangaroo. That is not at all the way this works. So the way that this has been measured, Haman Bhargava is the main person who has been running this thing, and so it was out in this paper. He was speaking in my seminar a few weeks ago. So the kangaroo example comes from him. It's an actual example. I'm not making it up. So you do an actual extensive search over all the single token substitutions, and you look for what actually maximizes the probability, okay, on a specified target. And the point is that, unlike what we would expect happens from our biased human perspective, you find that the optimal control sequence are not at all semantically or syntactically related to either the input or the target. They're just basically some gibberish combinations of tokens. And so this is the idea. You have an input. You want to input a control, which is at most 10 tokens long, and you want to see which outputs you are able to reach. So there's going to be a certain region that you can reach. Reach means that the maximal, with maximal probability that will be the output, with a control of 1 token long, a control of 2 tokens long, and so on. And so one can stratify, and there are various results that they have. By describing these reachable sets, you have certain specific bound on the reachable output set for a self-attention head, and this has been tested on some particular architectures of large language models, on a certain data set, and with particular bound on lengths of text. But so there are various results. All of them are quite interesting, but I want to focus on two parts of the results, which I think are the most striking. One of them is that you can take the outputs that without your control sequence would be the least probable ones, and you can turn, most of the time you can turn them into the most likely one output with a control sequence of at most 4 tokens. And the thing is that the actual control sequence that does this maximization is usually gibberish. No absolute relation to anything linguistically viable. So somebody is trying to convince me that this is a theory of language. I mean, are you fucking kidding me? I mean, right? Okay, so that's the thing. This can be, and I believe are, a useful experimental apparatus for trying to understand certain aspects of the question of how syntax interfaces with models of semantics. And there can be interesting questions that can be addressed, but this has nothing to do with being a theory of language. Okay, so what you allow me another famous quote, what is to be done? And well, we're scientists, so the one thing that we can try to do is actually do some science. So what I think can be done are 2 kinds of things. One is the one that I already described. So try to actually take seriously this idea of a non-behavioristic kind of a circuit investigation, where you actually have some specific model hypothesis of what type of computational structures you want to find, and you try to see how these are actually embedded into the architecture of transformer, and to what extent they can be embedded, whether they are perfectly or imperfectly embedded, and what are the limits of this computational model realized in the transformer architectures. And the other approach is to actually have a direct comparison of the mathematical models of what is happening. And the mathematical model of the of the generative grammar and the generative process of syntax is the one that I've been entertaining you in excruciating details for 27 hours. And the large language models, there are actually currently some very good mathematical models of how they function. They are based on the Zelig-Harris distributional model of language, because this is what the large language models are built on. So but they're kind of based on a modern category theoretic version of the Zelig-Harris model. And they basically these papers, that one of them has just come out a few days ago on the archive. And I think this is actually serious and respectable work. It's not about the theory of language. It's about the theory of what large language models are computing. It's a mathematical theory of what large language models are computing. And there is empirical evidence from the people here of the Amazon AI large language models that actually verify this theoretical model in the actual large language model architecture. So that's good, because it means that we have available a mathematical model of language as produced by human brains. And we have available a mathematical model of language as produced in large language models. So, there's at the theoretical level, one can compare these models at the level of mathematical models. What maps to what, and to what extent, how much of one is reconstructible from the other. And this is, the underlying theoretical question, if you wish. Okay, so I'm just gonna conclude with a kind of metaphor. I mean, I've been, to some extent, using theoretical physics often as a kind of guideline for how to think about certain questions in linguistics. But I think there's a more philosophical level at which one can use the lesson of the interaction between mathematics and theoretical physics to think about this question about theory and predictions and experimental apparatuses then in the context of language. So no, let's take the metaphor of what is happening in physics when you look at quantum field theory. I mean, quantum field theory is, as I mentioned before, the most precisely verified ever theory of physics. So, if there's anything that one can that stands on very solid ground from the point of view of the interaction between theoretical and experimental physics, it's quantum field theory. It's also very rich in terms of corresponding mathematical structures. The actual mathematical structures of quantum field theory are still by and large being investigated, and they keep producing new and interesting results. So it's a very good model to look at, of healthy interaction between several parts of science. So in quantum field theory, as I had spent some time discussing a while back, you have also a kind of generative process of combinatorial structures, which are the Feynman diagrams of a certain quantum field theory. And to each of them, you have an assignment of a corresponding meaningful physical values up to this procedure of renormalization that we have somehow used as our model of the syntax-semantic interface. So, for example, right, one of the things that quantum field theory predicts for you is the kind of perturbative computations where you can manifestly see the effect of the presence of a Higgs boson. So, when you talk about the Higgs boson production cross sections, it means that there are certain processes in your quantum field theory that will involve a Higgs boson being produced and then decaying into other particles. So when people, of course, the big news of a number of years ago, in particle physics was the discovery of the Higgs boson. What does it mean? It's not like, you go, hi, hello, I'm the Higgs boson, right? I mean, what is it that you see? You don't see, Higgs boson now and say, hello, I'm here, right? So what you see is something that has to do with these predictions made by quantum field theory. Okay, so what is that something? So you have an enormous experimental apparatus, which is a particle accelerator and it has detectors. And what this enormous experimental apparatus is doing is also solving an inverse problem. And what that inverse problem means here is that you want to identify inside an enormous set of data traces of the correct diagrams and processes that will involve the creation and decay of a Higgs particle. And so what you are effectively seeing is an image of the quantum field theory object embedded into this set of data collected by detectors and against a huge noise of background of other random events. So it's a kind of probabilistically smeared out signal that you see in the data. And what is going on, you can think in these terms, about what is going on with the computational process of syntax and what is happening in the large language models. You have this generative process of syntax. It's embedded in the large language model in a conceptually similar way. That its images sort of scattered into this probabilistic smear of weights and vectors in your transformer architectures that is trained over some large data set. And you are trying to detect signals of linguistic structures detectable inside this background of probabilistic noise. So, if you think of it this way, it's not like the large language model invalidates the theory of language anymore that a particle accelerators don't invalidate quantum field theory. It's actually the other way around. They are the experimental apparatus that confirms the predictions of quantum field theory. If one makes the right predictions and one looks for what one predicts. And so these are not, so the experimental apparatus itself is not the theory. A particle accelerator is not a theory of elementary particles. And they are an experimental apparatus for the study of a certain particular inverse problem that allows you to see the effect of theory embedded in the data. Okay, so the final line of basic wisdom is that data and technology without theory do not constitute science. And although it's sort of fashionable to claim otherwise, it is simply not true. And the point is, the purpose of science is the explanatory power. The fact of having a theory that makes prediction is just a test, is the falsifiability test that allows you to tell, be able to tell between different models which one is more accurate. But the explanatory part is not in the data, and it's not, it's coming from the theory. And so a theory of language is something that whose aim should be to produce explanations about the structure of language and the functioning of language. And this can be done so one of the point, of course, you can say there are different possible theories of language, and that's certainly true. There are different forms of linguistics and different theories of language. If you actually want to, or if you value the fact that a theory should be formalizable in mathematical terms, and that you should be able to approach science, other sciences like linguistics, from the same point of view of theory and methods that, in the way that you approach theoretical physics, then your choices narrow down considerably. And, effectively, generative linguistics become more or less the only game in town, because it's the theory of language that allows you for a treatment that, uses by and large the same philosophy, the same methods, and the same, principles as, the studying of theoretical physics. Of course, one can philosophically try to argue that they don't want, or they don't want linguistics to be studied in the same way as theoretical physics. This, is a philosophical position, and people are free to argue about it. But if you think that that is something valuable about the science, then that leads you in a certain direction in terms of how to try to model it. Okay, so this is pretty much the conclusion of everything that I wanted to say. And of course, I've presented my view of things. I have too much skin in the game to be the impartial external observer of the situation, and due to various events of life and so on, I feel compelled to take the moral responsibility of speaking on behalf and in defense of my co-author in this matter. And so that's where I stand. My point of view is entirely transparent and entirely obvious. But I give you, as I said, the dissenting opinion with respect to other kind of manufactured consents that populate the community. I mean, I am personally actually very much in favor of the development of artificial intelligence, for other kind of philosophical and ideological reasons that have nothing to do with this discussion about language, so that have nothing to do with this discussion here. But I mean, what I worry about is not so much the artificial intelligence, is the sort of legion of natural stupidity that rally around it, and this is somehow what becomes problematic. So unfortunately, if the game is to bring out all the swords, I have one too, and I'm perfectly happy to use it. But but okay, there's hopefully like a better approach to this kind of questions, which is based on actually doing science in the way of theoretical models, hypotheses, and experimental verifications. So I'm just gonna end here.
Have there been any experimental designed to use this kind of syntactical structure